Greetings and salutations, everybody. This is Jacob. Alright, so how the heck do we go about solving this problem? To say that it looks complicated is an understatement, my friends. Although I can't say for certain if it's as complicated as it looks, I can say one thing with certainty. There's quite some work involved in solving this problem, my friends. Oh yes. So let's get right to it, shall we? Let's start out by making a few definitions. Let's call A the set of people who get a Freddo espresso. Set B is the set of customers who get a cheesecake. And set C is the set of customers who get a bottle of water. We'll be making use of the algebra of sets. So A intersection B is the set of customers who get a Freddo espresso and a cheesecake. A intersection C is a set of customers who get a Freddo espresso and a bottle of water. And B intersection C is a set of customers who get a cheesecake and a bottle of water. From the initial conditions, we know that A equals to 112 customers, B equals to 77 customers, but C was given to us as a percentage. We don't actually have the number of customers who get the bottle of water, so let's call X the total amount of customers. It's unknown since the initial conditions don't mention anything about the total amount of customers. So we'll treat the total amount of customers as a variable, as an unknown. So since X is the total amount of customers, and the amount of customers who get a bottle of water is C equals to 70 times X over 100, or 7X over 10, since 70% of customers get a bottle of water. We do the same thing with the set of customers who get Freddo and a cheesecake, which is A intersection B equals 40 times X over 100, which is 4X over 10. A intersection C is 85 customers from the initial conditions. What's the next initial condition? It says that 90% of customers get at least one of these three items. So how do we express this mathematically? Let's turn our attention to this Venn diagram here. So the set of customers who get at least one of these items is all this stuff here, all these people here. And this is what we call A union B union C. So since 90% of customers get at least one of these three items, then we have 9 times X over 10 equals A union B union C. And there's a formula that expresses A union B union C in terms of these smaller sets. And that formula is A union B union C equals A plus B plus C minus A intersection B minus A intersection C minus B intersection C plus A intersection B intersection C. So we plug in the initial conditions and we get 9x over 10 equals 112 plus 77 minus 7x over 10 minus 4x over 10 minus 85 minus B intersection C plus A intersection B intersection C. So notice we have three unknowns in this equation. B intersection C, which is a set of customers that get a cheesecake and a bottle of water. That's unknown since we weren't given that information in the initial conditions. And also A intersection B intersection C, which is a set of customers who get all of these three items. We don't know that either. So now we have three unknowns. And what do we do when we have an equation with three unknowns? You guessed it. We set up two more equations. So we need two more equations, my friends. So moving on to the next initial condition, what does it say? It says 14 customers get exactly one item. How do we express this mathematically? So let's take a look again at the Venn diagram. The set of customers who get exactly one item are all these people here. And technically this set is written as this expression here, but we'll call this set exactly one item for brevity's sake. So how do we express this set in terms of these smaller sets? It's A plus B plus C minus 2 parentheses A intersection B plus A intersection C plus B intersection C plus 3 times A intersection B intersection C. So how the heck did we derive this equation? How does this exactly one set equal all this? Okay, when we added A plus B, we added A intersection B twice. So we have to subtract it twice from exactly one because we don't want it. So far we have A plus B plus C minus 2A intersection B. So we use the same logic with the other sets. We added A intersection C twice when we added A plus C, so we subtracted twice, and so with B intersection C. Now let's look at A intersection B intersection C. When we added A plus B plus C, we added A intersection B intersection C 3 times. And we subtracted it 6 times when we subtracted all those other sets. Since we don't want A intersection B intersection C in the final result, the net addition has to be 0. So since we added it 3 times and subtracted it 6 times, we have to add it 3 times in the final result. And we plug in the initial conditions and we get 14 equals 112 plus 77 plus 7x over 10 minus 2 times 4x over 10 plus 85 plus B intersection C plus 3 times A intersection B intersection C. And this is our second equation. 2 down, 1 to go, my friends. We need one more equation. Let's look at our next set of initial conditions. What does it say? It says 83 customers get exactly 2 of these items. So how do we express this mathematically? Let's take a look at the Venn diagram again. The exactly 2 set are all these people here, and technically this set is written as this expression here. But for brevity's sake, we'll call it exactly 2, like we did before. And this is A intersection B plus A intersection C plus B intersection C minus 3 times A intersection B intersection C. And we subtracted A intersection B intersection C 3 times from the final result because we added A intersection B intersection C 3 times when we added the first 3 sets. So we have to subtract A intersection B intersection C 3 times since we don't want A intersection B intersection C in the final result. And we plug in the initial conditions like we did before, and we get 4x over 10 plus 85 plus B intersection C minus 3 times A intersection B intersection C equals 83. And this is our third equation. So now we have 3 equations. For brevity's sake, let's call B intersection C y, and A intersection B intersection C equals z. So now we have this system of equations to solve. So let's start solving it from the third equation. We solve for y, and we get y equals minus 4x over 10 minus 2 plus 3z. We plug that into the second equation. We solve for z, and we end up with z equals 7x over 30 plus 3. And we plug this and our previous result into the first equation, and we now have an equation with just one variable, x. We solve for x, and we end up with x equals 150. So the total amount of customers is 150 people per day. 1 down, 2 to go. So we plug this in our second result, and we end up with z equals 38. And we plug in 38 and 150 in our y equals 52. So now that we have all this information, now we can answer the final question. How many customers only get a Freddo Espresso? Let's look once again at the Venn diagram. The customers who only get a Freddo are all these people here. And how do we express this mathematically? It's A but not the union of A intersection B and A intersection C. And this is A minus A intersection B minus A intersection C plus A intersection B intersection C. We add the A intersection B intersection C in there once because when we subtracted A intersection B and A intersection C, we subtracted A intersection B intersection C twice. So we have to add it once. So without further ado, the only espresso crowd, the number of customers who only get a Freddo Espresso after we plug in all the numbers equals 5. And that's our answer. 5. Only 5 customers only get a Freddo Espresso, which is an intuitive answer, if you ask me, given that only 14 customers get exactly 1 item. I mean, even if you guess it or ballpark it, you still have to prove the answer by doing all these calculations, my friends. Wow. Just wow, you guys. This was a revised and beefed up version of the first ever puzzle that I posted on this channel, which was an epic failure on my part. So I had to redeem myself somehow. And so this problem was born out of the ashes of that epic failure. I made some cosmetic changes to the problem. I turned the hot espresso into a Freddo Espresso, a cold version of the regular espresso with ice in it, which is quite popular here in Greece. You should try it out sometime, my friends. It's quite the treat. You don't know what you're missing. Oh yes. And I turned the cheese pie into a cheesecake. I love cheesecakes. And I changed the initial conditions, of course, quite a bit. And out came this monstrosity of a problem. Oh yes. If you can solve this percentage problem, then you can solve any other percentage problem in your sleep, pretty much. You'll be able to manipulate sets and percentages like nobody's business. Oh yes. So I hope you liked this puzzle. If you did, then smash those buttons like they owe you money. You know the drill, my friends. I could use the algorithmic help. And again, if you have any puzzle suggestions, then send them my way. I'm more than happy to showcase a puzzle that you're fond of. So that's pretty much it, you guys. I'll see you in the next video. Bye-bye.